I'll cover velocity analysis, which is an extension of the motion analysis discussed last time. Similar to the motion analysis, we need to define the vector loop equation and the nomenclature for a 4-bar mechanism. So as you see in this top image here, we've got the 4 bars. We've got link 1, link 2, link 3, and link 4. The length of link 1 is A, and that's a known value. The length of link 2 is A, and that's a known value. The length of link 3 is B, and that's a known value. The length of link 4 is C, and that's a known value. And the length of link 1 is D, and that's a known value or an input to the system. We can align our global coordinate system X and Y along link 1 to simplify this problem. And then our a nomenclature for our angles are the following. We go counterclockwise from the X coordinates, theta 2, theta 3, theta 4. Again, theta 4 is measured from the tail of link 4, and then theta 1 is 0. So this is our vector loop nomenclature. And at the bottom, what we have is the velocity. So what you'll see here is the velocity of link 2, velocity of link 3, velocity of link 4, velocity of link 1. Now, conveniently, the velocities are just the first derivative with respect to time of the position. So you see here we've got the vector, and we take the derivative with respect to time of that vector. So we've got the x component and the y component, and we take the derivative of the x component. We end up with this negative a times omega 2 times sine of theta 2, a omega 2 cosine of theta 2. So this is the angular velocity of link 2. Similarly, with vector 3, we have negative b times omega 3 times sine of theta 3, and the y component is b omega 3 cosine of theta 3. Also, this is the angular velocity of link 3. We take the derivative of link 4, x component, y component, and the derivative of link 1, x component, y component. If you look back in your notes, you'll see this vector loop equation is the same. What we've done is we've taken the derivative with respect to t. The derivative of 0 with respect to time is still 0, so we have velocity 2 plus velocity 3 minus velocity 4 minus velocity 1 equals 0. So similar to the motion analysis, what we're basically saying is these links can move in space, and the net displacement in this vector loop is 0. And the links can move in space at a rate, and when we go around this link, the net velocity is 0. So this is the velocity vector loop equation. Now, taking the velocity vector loop equations and components, x components and y components. So here are the x components and here are the y components. We can substitute them into the vector loop equation. When we substitute them into the vector loop equation, we collect the x components. We have this first expression. So again, this is v2, this is v3, this is v4, and this is v1. v2, v3, v4, and v1. Important to note that the summation of those velocities equals 0 in both x and y, right? So that adheres to this velocity vector loop equation. The next thing we can do is simplify. So we know two things. We know that the angle of link 1 is 0, and we also know that the ground link is not moving, so omega is 0. So when we simplify, we end up with velocity 2, velocity 3, velocity 4, and now we can simplify this expression. Negative d omega 1 sine of theta 1, this goes to 0. Similar, velocity 2, velocity 3, velocity 4, 0. So after we simplify that, we end up with these two expressions, and we can solve these two expressions simultaneously. When we solve these two expressions simultaneously, we end up with these two values. So we've got how theta 3 is rotating and how theta 4 is rotating. Now, the signs work themselves out. We determined that positive velocity is counterclockwise, and a negative velocity is clockwise. So the velocity of link 3 is A times omega 2 over B divided by sine of theta 4 minus theta 2 times sine of theta 4 minus 2 divided by sine of theta 3 minus theta 4. What you will see here is this is a single value. This is a single value. If you remember back to position analysis, there was omega 3, 1, 2, and omega 4, 1, 2. So there were two valid expressions for position. There is a single valid expression for velocity.